Dear students, today we will we will continue the topic of dimensional analysis. And today we will discuss certain non-dimensional parameters. As I told you earlier, that when we want to construct a model of a prototype, then we should try to reduce the number of parameters involved in the problem. And the one way to reduce the number of parameters is to non-dimensionalize the mathematical equation. And when we non-dimensionalize an equation, then some non-dimensional numbers are introduced in the problem, which are helpful in recognizing the flow pattern or many other properties of the flow problem. You know that in flow problems there are certain types of forces involved, like inertia force, viscous force, gravity force, pressure force, elastic force, etc. Stokes was first who introduced the non-dimensional numbers when he was studying the flow problems in the presence of some objects. In non-dimensional numbers, we have the non-dimensional numbers we have the ratio of certain variables involved in your problem. So I'll start with some non-dimensional number. First of all, I take the Reynolds number. It is very important number which predict about the flow pattern in many engineering problems. It is written as RE. This was introduced by Reynolds in 1883, and it is defined as ratio of inertia force to viscous force. As you see that in this number, inertia force, which is responsible for the motion, or you can say that inertia is the characteristic of an object, or you can say the fluid which resist any change. So it is related to the movement. Likely the viscous force, this produces the resistance to the motion. So overall, Reynolds number involves the forces which are related to the movement, and therefore at the end of this Reynolds number you will see that this Reynolds number determines whether the flow is laminar or your flow is turbulent. So I would like to derive its final form. You may write inertia force as mass into acceleration, and viscous force as shear stress into cross-sectional area. Now this mass is further density into volume, because density is mass per unit volume, so mass can be written as density into volume, and this acceleration may be written as velocity divided by time. Likewise, this shear stress may be written as viscosity into velocity upon length dimension. How can I write it in this way? You know that tau is equal to mu du dy. So mu represents viscosity, u represents velocity, and y represents length dimension. This is the length dimension. And next is cross sectional area. In this calculation you have to keep in mind that we will not cross the terms in numerator and denominator every time, but many times we will retain them because I have to make the standard combinations. So this density into this volume may be written as cross sectional area into length dimension, then velocity upon time. And then this is viscosity into velocity upon length dimension, and then cross sectional area. Now again density. This cross sectional area may be written as this cross sectional area will be cancelled with this cross sectional area, and write this length dimension as velocity into time. Here also I have velocity divided by time, and this is viscosity into velocity, and take this length dimension in the numerator. So length dimension. So finally you may cross cancel this velocity with this velocity, you may cancel this time with this time, and now you are left with the density that is represented by rho, velocity that represented by v or u, length dimension means L, and then viscosity that means mu. Again you may combine these two and you may write VL upon nu, which is the kinematic viscosity. So this is the ratio of inertia force to viscous force. Inertia force is governed by velocity and viscous force is governed by mu. You may very well check the dimension of RE. The dimensions of RE, Rayleigh number, it will be 1. As I told you earlier, dimensions of Rayleigh number will be 1. So here this L is characteristic length, V is characteristic velocity, and this nu is representing the kinematic viscosity. So this is the Reynolds number. Now this Reynolds number contains inertia force as well as it contains viscosity. So it is containing both the static and kinematic properties of fluid. This is the first point. The second point is that it specifies the flow pattern because it is related to viscosity, which is producing the resistance. It is related to V, inertia force, which resists the changes. So it specifies the flow pattern. And one of the controlling parameter of this Reynolds number is this viscosity. Now you see, if this inertia force is dominant to the viscous flow, that means RE is greater than 1. Then what will happen? Because inertia force is dominant and viscous force, which is producing the resistance, is not so powerful, therefore the turbulency will arrive in the flow region. So you can say that when Re is greater than 1, this implies turbulence. Though I will tell you the range for Re, or the value of Re for which the turbulency will occur. Flow is turbulent, and if your inertia force is weaker than the viscous force, then these type of flows are called the creeping flows, and are also recognized as laminar flows. Here turbulence occurs and here flow is laminar. So there are certain ranges. If I write the specific ranges, then in case of flow in a pipe, if your Reynolds number is greater than 2000, then this implies that flow is turbulent. And if Re lies between 10 raised to the power 5, 10 raised to the power 6, it refers to turbulent flow over a flat plate. Flow is turbulent in pipe. Yes, here it is written. Then flow is turbulent. It is a flow over a flat plate. So for internal flow in pipe, if I talk about the exact values or exact range, for internal flow in pipe, if Re is up to 2300, it is, if Re is less than or you may say equal to also, then this implies that flow is laminar. Okay, and if Re lies between, Reynolds number lies between 2300 to 4000, then this is the transition phase. That means now your laminar flow is preparing to be converted into turbulent flow. So this is the transition phase, and as your Re becomes greater than 4000 or equal to 4000, the flow becomes turbulent. If Re tends to infinity, then naturally your viscous forces are negligible. Very clear from its expression. Viscous forces are negligible, and naturally in this case your Eulerian equation of motion converts to this form. Rather, this is the conversion of Navier-Stokes equation of motion, because in Eulerian equation you already do not consider the viscous force. So this is the equation of motion, and if Re is strictly less than 1, then inertial forces are negligible. Inertial forces are negligible, and this is called the creeping flow. And in this case your equation of motion takes the form mu delta 2q minus delta p plus f. F is representing the body forces. So this is something about Reynolds number, and these are certain properties of these Reynolds number. Similarly, there are so many non-dimensional numbers which may be introduced in the flow problems according to their characteristics. For example, we come to another number which is known as the Froude number. This Froude number is written as Fr, and this is defined as inertia force to gravity force. Again, you can write this inertia force as mass into acceleration, and gravity force may be written as mass into acceleration due to gravity. Now this may be cancelled. This acceleration is velocity divided by time, and we will write this acceleration due to gravity as g. So this is velocity upon g into time. Again write velocity into g into, this time may be written as linear dimension, which we say displacement, upon velocity. Now combine this velocity with this velocity. This is velocity square upon g into linear dimension. So finally you get v square upon gl. So this is the Froude number. Again, you may check very well that the dimension of this Froude number is, there is no dimension of this Froude number. It is dimensionless. So it is another parameter, another non-dimensional parameter which is introduced in problems. As such, this Froude number is written as Fr is equal to V upon root GL. This is the actual expression for Froude number. Now if I talk about the characteristics of the Froude number, then Froude number comprises of both the dynamical and kinematical properties. It is related to force, so it is related to dynamical property, gravity force. It is related to velocity, so it is related to dynamical properties. So it contains both the properties. This Froude number is important when your gravity force is a dominant force in comparison to the inertia force. Further, it is very important to analyze the flow in spill wells, weirs, channel flows, rivers, and in ships designs, because it is used in calculating momentum transfer. It is used to calculate the open channel flow and the surface behavior of the waves. Now, for water measurement in open channel flow, Fr should be less than 0.5, because in this range surface waves will create no disturbances in the head reading. So if you want to measure the water in the open channel, Fr should come out to be less than 0.5, otherwise the disturbance will be created by the surface waves. It is also categorized as Fr is equal to 1. This is known as critical flow. Fr greater than 1, it is called supercritical flow. This implies super subcritical flow, and it is characterized as fast rapid flow. In such type of situation, the surface waves, small surface waves, will be carried downward. Then Fr less than 1, this is known as subcritical flow, or it is also called slow or tranquil flow. In this case, the small surface waves moves upstream in Fr if Fr is found to be less than 1. So in critical flow, your disturbances to the surface will remain stationary, because the velocity is just equal to the velocity of water will be, in such case the velocity of water will be just equal to the velocity of the surface waves. So these are certain characteristics regarding the Froude number, and naturally, as I told you earlier, this is important where the gravity forces are important. Likewise, you can derive Euler number. This Euler number is written as EU, also known as pressure coefficient, and this is the ratio of pressure force to inertia force. After certain calculations, as I did in Froude number and in Reynolds number, you come to an expression P upon rho V square. So this is the ratio of the pressure force to the dynamic force. It is P. Okay. It is important if the pressure force is a dominant force. First characteristic of this pressure coefficient or Euler number is that pressure force, if pressure force is dominant force, then it is an important number. And the inverse of this Euler number is known as Rouart number, which is denoted by Ru, and this is nothing but rho V square upon P, or 1 upon EU. When the dynamical forces are prominent, then Rouart number is important. This Euler number is used to characterize the energy losses in the flow. Okay, and it is also known as pressure coefficient, as I wrote earlier, but in that case it is denoted by Cp, which is taken as P minus P infinity upon rho V square P minus P infinity upon P naught minus P infinity. Here P is the static pressure, P is static pressure, at the point where the pressure coefficient is to be evaluated. P infinity, it is the static pressure at the point of evaluation. P infinity is the static pressure in free stream. That simply means it is remote from any disturbance. And P naught is static pressure at stagnation point. You know what is a stagnation point? It is the point where the velocity comes to zero, your flow stops. So it is the pressure, static pressure at the stagnation point. Now if EU or your Cp is equal to 0, it simply means that P is equal to P infinity. That means your pressure is equal to the free stream pressure. Similarly, if EU is equal to Cp is equal to 1, this means P is equal to P naught. So your pressure is equal to the pressure at the stagnation point. If EU is greater than 0, first I'll take the case EU is less than 0. If your EU is less than 0, this is negative. You know that pressure in the inward direction is taken as positive. And if it is giving you the negative value and this is positive, so simply P is negative, that means it is in this direction. So in this case, the contact of the liquid with the object will disappear and the cavitation will occur. So this is the condition for cavitation to occur. Cavitation occurs. Therefore, when EU is greater than 0, we say that flow is locally fully liquid. That means there is no cavitation. Similarly, there is another condition. If you get your Euler number or the pressure coefficient to be greater than 1, this means that free stream flow is compressible. So it is the condition of compressibility also. Free stream flow is compressible. So these are certain characteristics of Euler number. Similarly, you may find some more numbers which are important, like I am also taking another number, that is the Mach number. This Mach number is denoted by M, and it is the ratio of velocity past a boundary to the local speed of sound. It is the ratio of object speed to the speed of sound. It is written as V upon C. Many times it is written as V upon A. Here the V is the object speed and C is the speed of the sound. This number is very important in case of the objects which are created to fly in air, like the aeroplanes, the different types of aeroplanes, like the jet planes and many other. In this Mach number, due to local speed of sound, this is the local speed of sound, Mach number depends upon surrounding medium in specific temperature and pressure. That means at some specific temperature and pressure, what is the behavior of the surrounding medium is very important in Mach number. That medium in which your object is placed may be either a liquid or a gas. Medium may be flowing, boundary may be stable. Boundary may be flowing, medium may be stable, or both the boundaries and the medium may be moving with some relative velocity. So Mach number is important in the situation where you have some object and you have some medium. Clear? Now if this Mach number, I am writing the exact values. If it is less than 0.8, we say that the flow is subsonic. When commercial aircrafts are built with rounded nose and leading edges, then those go into the category of subsonic aircrafts. In these cases, the compressibility may be ignored. So a type of aeroplanes are called, these are the subsonic planes. Now if m lies between 0.8 to 1.3, 1.3, then it is called transonic. In these type of aircrafts, the wings are swept wings, and then in such cases the compressibility is important. Next is the category when m is equal to 1. These are called sonic. This is also a category where the speed of sound is equal to the speed of object. Many times it is recognized as transonic flow, because in some books you may get that when m is at 1, naturally one is lying in this region, one is lying in this range, but still up to 1.3 you may say that it is transonic. Now when it is 1.3 to 5, these are supersonic. In these, compressibility is important, shock waves are generated, and no upstream influence is there. So compressibility becomes important, shock waves are generated, and no upstream influence is there. When m lies between 5 to 10, this is known as hypersonic. Again, compressibility is important, shock waves are also there. When m is greater than 10, this is called hypervelocity. Hypervelocity. If I talk about the space shuttles, then when space shuttles re-enters the atmosphere, then the heated atmosphere becomes ionized plasma or gas, and spacecraft must be insulated from the high temperature. So in that case, m is equivalent to 25. So you see, this is the stage where due to your heated air, the temperature is so high that your heated air becomes ionized plasma, and therefore it is the spacecraft is to be built in such a way that it should be safe for that much of temperature, and so it should be insulated for the temperature. So you see that this Mach number is very important in compressible flows. Square of Mach number, that is m square, is known as Cauchy number. As Mach number is non-dimensional, c is also non-dimensional. So this is all about Mach number. You may also find what are other uses of Mach number, and in this way you may find certain non-dimensional numbers like Eckert number, Peclet number. There is another number which is the Prandtl number. This is Prandtl number, which is denoted by PR. It is also an important number, and which is related to the momentum diffusivity divided by thermal diffusivity. So being the ratio of two diffusivities, naturally it is the non-dimensional number, and it is written as expression as mu Cp upon kappa, where kappa is thermal conductivity, mu is viscosity, and Cp is Cp is a specific heat at constant volume. So it depends upon the fluid and the fluid state. It does not depend upon the length scale. So you are seeing there is nothing related to the length scale. It is related to fluid and the state of fluid. For most gases over a wide range of temperature and pressure, PR is constant. This is its characteristic. And it is used to measure the thermal conductivity of gases at high temperature. There the Prandtl number is very important. If your Prandtl number is strictly less than 1, then naturally thermal diffusivity dominates, because this is bigger than momentum diffusivity. Then this implies thermal diffusivity dominates. Heat conduction is significant compared to convection. Like in mercury. In mercury, heat conduction is very important. And if PR is greater than 1, then momentum diffusivity dominates. Momentum diffusivity dominates. Like in engines, where the transfer of energy is effective through convection, not through conduction. And when PR is equal to 1, momentum and heat both dissipate at the same rate, because momentum diffusivity is equal to thermal diffusivity. So both dissipate at the same rate. In liquid metals, this is true for liquid metals, because their thermal diffusivity is dominant. Here the heat diffuses quickly in metals, so PR is strictly less than 1. And PR greater than 1 may be the case in oils, where heat diffuses very. So like these numbers, you may also have Eckert number, you may have Peclet number, Weber number. These are certain numbers where Eckert number is written as EC, denoted as EC, and this is equal to V L upon CP T. If I talk about Peclet number, this is denoted by PE, and this is equal to VL rho Cp upon kappa, thermal diffusivity. So it is important in the fields where temperature is taken into consideration. And Weber number is written as We, which is equal to rho V square L upon sigma. It is the ratio of inertia force to surface tension force. This is the surface tension. So these are certain numbers. Similarly, you can find certain numbers for the compressible type of flow and many other types of flows. And you may search about their importance, Eckert number, Weber's number. And if I talk about their importance, then I would mention a very simple example to show that how these numbers are important. Suppose you have some oil of a specific gravity 0.85 density, sorry, it is a specific density of just a minute. This is oil specific gravity, or I can say it is the density. Okay, it is flowing through a pipe, and the diameter of the pipe is 5 centimeter. So what is it? It is the length dimension. It is flowing at a rate, it is the flow rate, flow rate is equal to 3 liter per second. So this is discharge, and if I convert it, I may write it as 3000 centimeter cube per second. Further, viscosity is given as 3.8 voice. So it is asked that find the type of flow. Now you see that what are the parameters involved in this problem. Here the flow rate is involved, here the viscosity is involved. So clearly this is a question of Reynolds number. We will calculate what is the Reynolds number, and then we decide that what is the type of flow. So what is Reynolds number? Reynolds number is VL rho upon mu. Now velocity is 3000. If I talk about velocity, it is 3000 centimeter cube per second. So velocity will be discharge upon area. Area is pi r square. Diameter is 5, so it is 5 by 2 square. So this will be the velocity because it is given the discharge into L. L means diameter into rho. Rho is given as 0.85 and divided by mu. Mu is 3.8. Solving it, I'll get 1.71. Because it is a non-dimensional number, there is no need to write the units. Just the units should be of the same category. Like it is centimeter, it should be also in centimeter cube. So it is, sorry, it is not 1.71, it is 171. This is 171. So it is less than 2300. It simply means that flow is laminar because it is the condition. For a flow to be laminar, that RE should be less than 2300. So this is the way how we judge the flow. Okay. In the same way, you will have questions. Some specifications of the models are given, some of the prototype are given, and you may find whether the prototype, whether the model is representing the prototype. You may find certain parameters which are missing from the prototype with the help of given specifications of the model and prototype, or likewise you may find the information about the model which is missing from the given information. So this is all about this lecture. Thank you.